Alright, review problems, part 3. Looking at these special triangles, these are things that I think you might remember me saying up front that it would be really helpful to know these two triangles. Again, we're not going to get into how we developed them in the first place, but essentially we have these two triangles here. We have one that is half a square, and that one's our 1, 1, root 2 triangle, where this was 45 degrees, or pi over 4. We also have our, let's try again. We also have our 30, 60, 90 triangle. That looks something like that. So that's 30, or pi over 6. This one's pi over 3, so you look at it sometimes from one angle, sometimes from the other. The short side's 1, the longest side's 2, and this one's square root of 3. So the three angles between 0 and a half pi, pi over 2, which you can use these special triangles, are these three angles, right? Pi over 4, pi over 6, pi over 3. And if you want them in order, I guess I could rearrange them here. That one's the smallest one. Pi over 3 is the biggest one. Okay? Second thing here, we'll have to come back to those triangles. Give 3 examples of angles in each of quadrants 2, 3, and 4, which you can also use these triangles. If you have other angles that have those as reference angles, you can use them. Right? So if you have any angles in these other quadrants, if you're looking at quadrant 2, if you have an angle where this angle's, that's pi over 3, then you can, with that angle, right? 2 pi over 3. 2 pi over 3, whoops. 2 pi over 3, or if you move this a little bit, if you move this a little bit, you have pi over 6 instead. Pi over 6. You get 5 pi over 6. Or the third one in that quadrant is going to be if you make that pi over 4. Okay, if that's pi over 4. Right, so if you have the reference angle as being those, you're going to have that as 3 pi over 4. That's the leftover. 3 pi over 4. So you got the 3 of them in each quadrant here for each of those angles. You can have 2 pi over 3, 4 pi over 3, and 5 pi over 3. So that's for quadrant 2, 3, 4. Related to 3/4, you're going to have 3 pi over 4, 5 pi over 4, 7 pi over 4. And then for the ones related to 5 pi over, related to pi over 6, that's pi over 6. You got 5 pi over 6, 7 pi over 6, 11 pi over 6. Right, all those angles that have those basic ones as reference angles. What is tangent of 5 pi over 6? If you want the tangent of 5 pi over 6, let's try that again, because I think I need to take those with me here. Let's try it a third time. Alright, so if we grab these triangles, we'll move them down here. Good to have this in mind. Okay. So we can refer to them here. If you're looking for what tangent of 5 pi over 6 is, you got to think and realize that 5 pi over 6, again, from up above here, 5 pi over 6 is related to pi over 6, right? 5 pi over 6 is right there. Reference angle is pi over 6. So you think first that tangent of pi over 6 is from this triangle here. From that triangle, it is opposite over adjacent. You have 1 over root 3. So then tangent of 5 pi over 6 is going to be exactly the same number. 1 over root 3, except it's going to be negative because it's in quadrant 2. Right? Negative, quadrant 2 over here. If you're looking for cosine of 5 pi over 3, again, draw it. It helps to draw picture of it, 5 pi over 3 is going to be in quadrant 4, all the way over there. That reference angle is pi over 3, so think in your head, cosine of pi over 3 is, we're going to look at it from this angle here now, right? Cosine of that is, you're looking at it from this point of view, pi over 3, we've got adjacent, that 1, over hypotenuse 2, right? So yeah, cosine of pi over 3 is 1 over 2. You're looking at quadrant 4. Okay, quadrant 4 cosine is positive. So we've got cosine of 5 pi over 3 is also 1 over 2. Easy, right? Determine the value of sine of 5 pi over 4. Well, we need this other triangle for that because this is the one that has pi over 4 in it. That triangle right here. Again, think about what quadrant it's in. Draw a quick picture of the thing, or keep that in mind. 5 pi over 4 is right there. That's 5 pi over 4. Think about 5 pi over 4, it's quadrant 3. Think first what sine of pi over 4 is, the reference angle. Sine of pi over 4 is, from that angle you got opposite hypotenuse, 1 over root 2. 1 over root 2. Sine is, in this quadrant, negative, right? So then sine of 5 pi over 4 is going to be same number, but negative. Now this is sort of working backwards here. If you're given a ratio, if sine theta is negative root 3 over 2, what angles could it be? What angles? So you're looking for the angles. You can get them by looking back from the triangles. First of all, again, think of what quadrant you're looking in. Where could it be? If it's negative, okay, it says that's negative. So it's got to be quadrant 3 or quadrant 4, right? That's where sine is negative. You could have one angle there. You could have one angle there. So you're looking for that angle, and you're looking for that angle. So we find each one here, one at a time. Let's find that one, and then let's find the other one in that quadrant, right? So which of the triangles is that related to? Well, let's grab this triangle again. We've got to look at which one has a sine of root 3 over 2. If we're looking at which one has a sine of root 3 over 2, let's clear this up a bit first. Okay, we want root 3 over 2, so this is root 3 over 2. It's got to be this angle, right? The reference angle has to be pi over 3. Okay, reference angle is pi over 3. So if you look at each one here now, if this little angle is pi over 3, then you got to be talking about either 4 pi over 3 if it's in quadrant 3, or if this little angle here is pi over 3, then 5 pi over 3. Okay, those are the two angles it could be. Now we'll look at graphs of these basic functions first before we look at reciprocal functions. Make some space here. Draw the graphs of the basic three functions. This should be something we're hopefully good at doing without too much trouble. We've already used them before for some of these questions. The basic three, we'll make this one a bit taller. Tangent, you need some more room probably. That's 1 and that's -1. The sine graph starts in the middle of a cycle, goes up, down, down, up, and it just keeps going. I don't know if I drew it all that symmetric, but its maximum is 1, its minimum is -1. From one point to the same point, one complete cycle of that graph. Okay, there's one complete cycle of that graph. That is 2 pi. The period of that is 2 pi. From 0 to 2 pi. In the middle is pi, and then you have the two in between points there if you need those. The period of that is 2 pi. The period of the cosine graph is 2 pi as well. Cosine starts at the top of a cycle. Let's make that a bit bigger so we can work with it better. Okay. It starts at the top of a cycle. It starts up at the top here and goes down and down there, back up, keeps going, right? Keeps going the other way as well. Make that a bit longer. If you're trying to label this thing, one complete cycle of this graph goes down, up to the same point again. That's the same point in this, alright? One cycle of that graph from 0 to 2 pi. Both of these graphs, sine and cos, that's y is sine of x, this is y is cos of x. Those two functions both have a period of 2 pi because that's how long it takes for one complete cycle to finish. Right? That distance is 2 pi. That's the period. Regardless of where you start. They both have a max and min of 1. Sorry, max of 1, min of negative 1. Right? The range is between 1 and negative 1. Tangent, on the other hand, we are gonna need some more space for this. Because this one goes above 1 and negative 1. Not that we're going to keep the scale the same, but we'll extend this a bit here. Tangent starts at 0. And by the time you get to pi over 2, it's undefined. It'd be good if you drew some asymptotes in there first for where these are going to be. So let's actually draw that before we do anything else here. Let's draw some vertical lines for asymptotes at pi over 2, at 3 pi over 2. Let's do another one here and fix the axis in a second. We'll do one on the other side. Let's try again on the other side. It's more or less looking like we want it to. So our tangent graph here looks like this. It starts going up. It actually just is asymptotic at pi over 2. That is pi over 2. And it goes the other way. It's symmetric on the other side here. It goes down towards negative infinity at negative pi over 2. Tangent is undefined at 90 degrees. Okay, because the x coordinate is 0. Right? Remember that tangent is y over x. Tan of whatever angle you're looking at is y over x. So anywhere that you're cycling around where the x coordinate is 0, you're going to have tangent being undefined. And then it just keeps repeating. There's a point in here that's pi. And you're going to have this same shape repeat itself. This is a really rough graph, and you're going to have the next asymptote at 3 pi over 2. At 2 pi, you're going to have another x-intercept. That same part of the pattern just keeps repeating itself. The difference here is that the period is pi, not 2 pi, right? Because one chunk of that graph is that long. It's from negative pi over 2 to positive pi over 2. The distance for that is thing. Okay, if we look at how far it is from one point to the same point, if you look from that point to the same point, that period is pi, not 2 pi. It repeats itself every pi. I can use the basic graphs to evaluate an expression such as 3 pi over 2. If you're looking at what sine of 3 pi over 2 is, if you look at the sine graph, again, you just draw the real quick sine graph here. Okay, that's kind of a terrible reproduction, but more or less something like that. You should know it more or less to be able to draw it that quickly. Divide it into those 4 pieces, right? Up, down, down, up. The 4 quadrants. And you can look at what sine of 3 pi over 2 is. There's 3 pi over 2. So it's sine 3 pi over 2 is negative 1. Use the graph just to look at the y values, right? Negative 1, it gives the y values. because that is a graph of y equals sine of whatever you put in. X is the angle, y is the ratio for that angle. Are the graphs of sine and cosine similar to each other? Period is the same. Okay, it's 2 pi. Range is the same. Oops, nice spelling. Range is the same. Range is between -1 and 1. Shape is the same. How's a graph of tangent different? Well, all these things are different, right? Tangent has a period of pi. Tangent has a range of all real numbers. If we talk about the shape, shape's totally different, right? And I left out the domain here. The domain for sine and cosine is all real numbers. For tangent, it's not all real numbers. It's all real except for certain values, right? Except for where the asymptotes occur, right? The asymptotes, if you want to write an expression for that, if you scroll back up here, if you look back at this, if you want to describe where the asymptotes are, here's the first one, and then they're pi apart. So you can start at pi over 2 and add multiples of pi to get to any other one. So the way of writing that expression is pi over 2 plus n times pi. So all real numbers except for that. Obviously you could make this list endless here. No asymptotes for sine and cosine, asymptotes for tangent, but those are the main things. Alright, we'll leave inverse trig functions for a minute and do that in the next part.